In this video, we're going to be looking at the kinetic theory model. And the main question I want to ask is, what is the connection between the pressure that is exerted by the gas molecules on the walls of this container and the speeds of the molecules? So what we want to do is come up with a derivation of the equation that relates the temperature and the molecular speeds of these molecules in the gas. So we're going to consider an ideal case. We have some cubical container where each side of the container is length L by L by L. And the box contains a number of N molecules in the container. And it's an ideal gas. And each of the molecules have the same mass, M. And we're going to recall maybe at this point maybe the kinetic theory model assumptions. So here are our main assumptions of the kinetic theory model. We're going to assume that the molecules of the gas are perfectly identical. They all have the same mass. We're going to assume that each of them undergo elastic collisions between each other or the walls of the container. So elastic, by the way, means that when they collide with one another at the walls, that the kinetic energy and the momentum is conserved. So the molecules only really have kinetic energy. We're going to assume that they don't have any potential energy, so they don't exert any forces on one another except during collision. So over here, I talked about how the forces between the molecules are negligible except during collision. So there's no potential energy, and so really all you have is what we call translational kinetic energy. We're also going to assume that there's the effect of gravity is ignored. Okay, these little molecules have very small masses. When these molecules are zinging around, they're moving in straight lines and they're going at constant speed. The motion of these molecules is random, all right? So some are going fast, some are going slow, all right? There are sufficiently large amount of molecules, and we're doing that so that we can apply the mathematics of statistics in here. But even though there's a lot of molecules, the molecules are very small in size relative to the distance between the molecules. So those intermolecular forces are don't really exist except for when they collide with the wall or with each other. And of course we're going to assume that the molecules have the standard physical properties of mass, momentum, and energy, and they basically obey Newton's laws of motion. So back to my derivation page here, and we're going to have just considering only one single molecule as it hits one wall over here. And I've made a little animation to try to help illustrate what we're going to be deriving. So I was playing around with GlowScript, and I just created this little program where I have a ball just simply bouncing along in between the walls of a container. And I gave it a velocity along the x and the y-axis, and I'm just keeping it along the z-axis at the same coordinate. But really, when you look at this molecule, it has velocities along the x, y, and z axes. So I'm going to just modify the ball velocity and only have it going with an x velocity here. And so we're going to keep a really simple model and just take a look at a molecule that is going just bouncing back and forth along the x-axis here. So we're only looking at the velocity along the x direction. We'll call that just say Vx right now. And we're not going to be looking at the y component or the z component, but we'll bring them in a little bit later on in our derivation. So just to keep a simple model here, we're going to be just looking at a single molecule over here that is going to be coming along and hitting the wall and then basically rebounding back here. Now remember that the molecule basically makes an elastic collision with the wall. So that means that the kinetic energy and the momentum is conserved. So if you recall from when you studied momentum, hopefully you recall that in a elastic collision, if it was coming in with a velocity v on the wall, then it's going to be coming back with the same speed, but it'll be now negative v. And I'm going to put a v sub x because we're going to be looking at only the x component of that velocity. So what we want to do is calculate the change in momentum of the molecule when it collides into the wall. So if we were trying to find the change in momentum of the particle, now you hopefully recall that momentum is mass times velocity. So the change in momentum, because the mass of the molecule is not changing, the change in momentum would be mass times the change in velocity. So this would be the difference of the velocity, so that like the final velocity minus the initial velocity. Now, if you look over here, the final velocity would be negative Vx, and the initial velocity would be Vx. And so that is a total change in momentum of actually negative 2mvx. All right, remember it has to stop it, so it loses that momentum mv, and then it has to throw it back the other direction, another mv, so that's why we have a whole change of 2mv. All right, so you might be wondering, why am I calculating the change of momentum? Well, you might recall back when you studied physics earlier that F equals ma, and that's the Newton's second law, which is also equal to m times change in velocity over change in time. And so if you cross multiply here, you'll have force multiplied by time is equal to m times delta v. So that is the impulse, right? The impulse or the change in momentum. So if we calculate the change in momentum equals m times delta v, we also know that is equivalent to force times time. So moving down in my notes over here, we're going to be calculating the force on that the single molecule applies on the wall. Now over here I have calculated the change in momentum for the molecule. So I would like to find the change momentum on the wall. And if you recall from Newton's second law, or actually Newton's third law, sorry, every action force has an equal and opposite reaction force. So just like that for momentum, every action momentum has an equal and opposite reaction momentum. So the change in momentum of the molecule, all right, whoops, that's not very well written here, is equal to the change in momentum of the wall, but except it's negative. So therefore, we can say that the change in momentum of the wall would be simply positive 2mv sub x. Okay, so why are we doing that? Because we want to find the force exerted on the wall. And the force exerted on the wall, if you recall from over here, is equal to the change in momentum divided by the change in time. So that change in momentum is 2mvx divided by the change in time. But I don't really like this delta t, and I kind of want to get rid of that. And so we want to find how long it takes in time in here. So how can we get rid of the delta t? Let's go back to our animation for a second. All right, so how long does it take? Well, remember that the length of the cube is L. So from it colliding with this wall and then coming back and colliding with the same wall, it's going to travel a distance of 2L in that time. So that molecule is going to travel a distance of 2L from this wall and then back to the wall again in that time. So if we go back down here in our derivation, we could say that, remember, velocity is distance over time. So it would travel a total distance of 2L in a time of delta t. So we want to rewrite delta t and get rid of that. So delta t would be equal to 2L divided by v sub x. So we're now going to substitute this expression in here right over there into the above equation. So the average force now from that one single collision from the one molecule is going to be 2mvx divided by this time, which we're going to replace that 2L over Vx. And you should notice that the 2's here cancel out, all right, and then you have a Vx. It's not canceling out with that Vx. It's actually going to be multiplying by that. So you're really going to end up with mvx squared divided by L. And hopefully a little bell rings off at this point, because mv squared, that's kind of similar to 1/2 mv squared, which is kinetic energy. So we're kind of getting there. So hopefully you can see there's some kind of relationship of kinetic energy. And then we got force here and length L. So we're going to go a little bit further. Now, we also have to consider the fact that this is only one single molecule, and there's a lot of molecules. There's n molecules. So if we were to try to find the total force from all of the molecules, say they were all going horizontally to the right, how would we calculate that? So let's say we were to find that total force. Well, you would have, like, say, mvx1 squared divided by L, and then you have mvx2 squared over L, and then you basically keep doing that until you get to mvx nth particle divided by L. So you get all these molecules. So really what it comes down to is you could just say there are n molecules multiplied by mvx. And there's a bunch of these guys, really. If you think of it, there's a whole slew of them, and some of them are going fast and some of them are going slow. So this is a mv x squared, but it's an average of them. All right, and later on in the notes I'll talk about that. That's the something we call the root mean square velocity, and that's all divided by L. So this Vx squared is the average of the squares of the velocities. Now the next part of our derivation is the fact that we're only looking at the force that's exerted on essentially the horizontal wall, because we're only assuming all the molecules are moving, say, horizontally. But we really want to look at the contributions of the velocity going in all the directions. So imagine you have this molecule M that has a velocity v, there is a Vx, there is a Vy component, and there's a Vz component. So there's really all three dimensions, x, y, and z. And there's symmetry in this problem. You know, we have a cube, L by L by L. So if you remember Pythagorean theorem, we're going to apply it in 3 dimensions. So V squared is equal to Vx squared plus Vy squared plus Vz squared. And since there's symmetry in this problem, that we could say that, you know, Vx squared, and let's bring in the average here, average of that squared, is the same thing as the velocity along the y component squared average. And that would be the same thing as the velocity along the z direction squared average. So they're all essentially the same because of symmetry in the problem. So essentially, if you were to find the resultant velocity v, you could say that it's basically 3 times the velocity of the square root of the velocities along the x-axis. So therefore, the Vx squared average, all right, is equal to 1/3 of V squared average. And we're now going to essentially replace this bit, all right, with this expression over here, because we want to find the force that is due to the molecules that are both having x and y and z components. So the net force now becomes, we're going to take this expression over here, n, the number of molecules multiplied by the mass of the molecule, and then the x component squared of the average of those velocities, and then divided by L. But we're now going to replace Vx squared, the average of that, with 1/3 of V squared average into that expression. So this becomes now the total net force. We'll have essentially a 1/3 in front of this expression. So we'll have a 1/3 nmv squared average divided by L. Okay, we're getting a little bit closer, and now if you can see a little lower here in the notes, we have to kind of bring in the idea of pressure. And if you recall earlier, we defined pressure as force divided by area. Okay, and if you hopefully recall that if you're talking about a cube here, the area of one side is just going to be L by L. So you could say force, the pressure is equal to the force over L squared. Okay, so let's put that in here. Now we're going to take that force expression up here, which is 1/3 nmv squared average, all right, divided by L, and then all of that divided by L squared. And so what you're going to end up over here with is a L cubed. So let's bring that L and L squared over to the other side, which is L cubed, and so you'll get P times L cubed. And if you recall, L cubed is just really the volume of the cube. So the pressure times the volume would be equal to 1/3 nmv squared average. And we've got this nice little expression there. Now that's kind of important because, well, we want to relate that to the ideal gas law. And let's also take the fact that this is an mv squared. So what are we going to do with that? Well, let's rewrite that a little bit. PV, and I want kinetic energy. And if you recall, kinetic energy is equal to 1/2 mv squared. So I'm going to do a little trick here. I want to make this into a half in here. So we're going to put a 2/3 instead, n, and then we'll have 1/2 mv squared average. Now you might be wondering, why am I doing that? Well, I'm really not changing this. I'm just, dividing this part by half, but then multiplying the front of the whole thing by 2. So it's really multiplying by 2 and dividing by half, or dividing by 2 here. And so I really not changing anything. But the key here is this expression here is the average kinetic energy. So I've now shown that the pressure times the volume is equal to 2/3 multiplied by the number of molecules multiplied by the average kinetic energy. And so we've just shown that the pressure times volume is directly proportional to the average kinetic energy. And if you recall from our notes earlier in chapter 14, let me show you that. We had two expressions for the ideal gas law, but this version I'm going to use. PV equals the number of molecules multiplied by Boltzmann constant multiplied by the temperature in Kelvin. So if we compare this expression with the ideal gas law, which is PV equals N times Boltzmann constant times the temperature, I'll just shift this down here. We can then say that 2/3 times the number of molecules times the average kinetic energy is equal to N, the total number of molecules, multiplied by Boltzmann constant times the temperature. And so you can see that the N's cancel out. And so 2/3 times the average kinetic energy is equal to Boltzmann constant times temperature. Or, often what you see on your formula sheet is the average kinetic energy is equal to 3/2 times Boltzmann constant times the temperature in Kelvin. So this is a very important expression. And this basically applies only for an ideal monatomic gas. And it's the reason why is that we're looking at only a single molecule, which has only translational kinetic energy. If you were to deal with a diatomic gas, where you have two molecules bonded together, and now you have also rotational energy. And when you start to consider the rotational energy, this 3/2 turns into a 5/2. But that's not part of the AP Physics 2 curriculum, so you don't have to worry about it. All of your questions that you will typically get in terms of calculating things will be assuming the gas is an ideal monatomic gas. So when we add energy into a monatomic gas in a container of fixed volume, all of the energy goes into increasing the translational kinetic energy, which then directly impacts the temperature in Kelvin. There's no other way to store energy in the gas other than increasing in its kinetic energy. So the total internal energy, I should point out, of an ideal monatomic gas becomes now 3/2 nRT. So this expression is the average kinetic energy per molecule. This over here is the total internal energy of the entire ideal monatomic gas. So hopefully you can see that from this derivation, we've shown that the temperature of the gas depends on the average kinetic energy of the molecules of the gas. And so, and we've derived this expression for the average kinetic energy is equal to 3/2 times the Boltzmann constant times the temperature in Kelvin. Now, not on the AP equation sheet, but a very helpful one to know, is U equals 3/2 times nRT. N is the number of moles. And then you can see that's just simply if you took this average kinetic energy and multiplied by n molecules and then rewrote it and got rid of number of molecules and using Avogadro's number and its relationship with the Boltzmann constant, you would get this expression over here of U equals 3/2 nRT. All right, so therefore the change of internal energy typically in a closed system where you're not changing the number of molecules or moles is really only going to be changing if the temperature changes. All right, in the next video I'll kind of dive into what is that V squared term. It's a special type of speed called root mean squared. But I'll leave that, this video is quite long, so I'm going to leave that for another video.